Mm-hmm.
Okay. Okay. Yeah. So this is really just kind of a high level overview, HDD, some applications and different considerations with the design. So I'll just jump right in. Maybe. Okay. Sorry, figuring this out.
You got it, Jim.
Is that it?
Yes, sir.
Okay.
For some reason. There we go.
Okay. Sorry, is it the back instead of the front? Same slide. Okay. So here's just a couple of the things we're going to look at. Just an introduction, kind of the overview, construction feasibility, which is kind of a big, especially on the front end. That's really a huge factor. There's a lot of projects that get out to bid and they're just, they've got a lot of feasibility issues and just causes problems for everybody during the whole project. Obviously HDPE pipe, which we're talking about today and focusing on that. And then some of the tooling and design tools that can be used on these projects. So courtesy of Mears, my former employer, we've got these cartoons that kind of illustrate kind of the basics of HDD. I'm sure everybody's seen this, crossing a river here, drilling a pilot hole. You know, depending on the soil conditions, you've got some sort of drill bit. That looks like a tricone for harder material, but can be used in soft material too. A lot of the medium to small projects, you're going to be using more of a fixed angled type bit for smaller rigs. So I'm sure you've seen some of those. So there's a lot of different varieties. This one has in this area, the non-mag collar. That's basically to remove magnetic interference to the guidance instrumentation that's attached down near the drill bit. Reaming or pre-reaming, that's just enlarging the hole to the diameter necessary to pull the pipe in. So, you know, after all these years, there's still a lot of, I don't know if confusion's the right word, but different opinions on the correct size hole. And it is a little bit of a means and methods question, but you see some requirements that are very much, you must drill this size hole for this size pipe. And that, in my opinion, that's probably not appropriate. You might want to say a minimum hole size. But typically on 24-inch pipe and less, holes are typically 50% larger than the pipe OD, and 20 or 24 above, it's about 12-inch larger minimum. So sometimes larger, some contractors like to go 14 inches. And then when you get up in the larger diameters, 36, 42 and above, sometimes that's even bigger because there's just more room for the pipe to move around and makes it easier to pull the pipe in. And then the pullback, one step in between here is swabbing, which is after the final ream pass to pull a barrel reamer typically through the hole. And that barrel reamer is typically the diameter between the pipe OD and the hole OD. So it's maybe like halfway between or something like that. And that's just really to verify that the hole is clean of cuttings and there's not any excessive torque or pullback. It should be pretty easy to pull that back. A lot of times on smaller pipes, this step is skipped, and that's probably okay. On, I would say anything 12-inch and above, it probably should be done. Some contractors will think, oh, this hole's great, it's ready to pull the pipe in. I think a lot of times that's probably true, but this is usually a really quick thing. You're going, 300 foot per hour, so even longer crossings can be done in usually less than one shift. So it's not a huge cost, but it's one of those things that you'll never say, I wish I didn't do that, but you might say, I sure wish I would have done it. So it's kind of a cheap insurance, in my opinion. But pullback, we've got obviously the pull head, swivel, reamer. That could be a barrel reamer. That could be a hole opener like shown there. So next phase, the design for HDD is really focused all around how the pipe is installed and the hole is drilled and the equipment limitations. So it's really you're designing really a construction process as much as the final product, because I mean, especially with HDPE, you're rarely designing the geometry around the limitations of the HDPE pipe itself, or shouldn't be. It's really about drill pipe, tooling, soil conditions, the depth requirements for the obstacle you're drilling under, and things like that. So entry and exit angles are really going to be based on what the rig can do. Typically, you really don't see entry angles too much less than 10 degrees, and maybe up to 20 degrees. For the smaller the rig and the smaller the pipe is, the steeper you can go without too much negative problems or whatever. But and another thing is you're trying to gain depth quickly, so that you've got more depth to cover and more overburden pressure to contain the drilling fluid pressure and minimize the frac outs or IFRs. Vertical radius is, especially for HDP, it's really based around the drill pipe, and for larger diameter pipe, say 24-inch and up, you're probably going to be looking at what the tooling is compatible with. So because when you go with those large diameter hole openers and reamers, you've got a lot of torque. And when you go from say a 36-inch reamer and you're using 3.5 to 5-inch, maybe 6-inch drill pipe, there's a lot of stress concentrated on those tool joints. And just to minimize excessive stress and potential damage to those, larger radii are much more compatible. Yeah, so like I said, the geometry is based on the rig. 12 degrees is typical for entry angle, exit angles. Kind of rule of thumb, 10 degrees on the exit, which makes it easier to handle the pipe above the ground there and get it into the ground. Not as much of a concern with HDPE pipe, but it does seem to be what works best. And of course, every project has its own constraints and limitations that will change that a little bit. Exit angle, I just said that. 8 to 12 is typical. The one on the upper picture there, that's steel pipe, of course. So obviously that's a great picture to promote HDPE pipe where that is appropriate. That's a 14-degree exit angle. And I think that pipe's held up in the air maybe right around 30 feet. So it's 24-inch steel. So obviously it's a major concern to make sure that pipe is not overstressed or damaged. And the equipment you have to have gets to be pretty expensive. Whereas on the other picture with the HDP pipe, it's just laying on the ground. I think that's a 16 or a 20-inch pipe. So good comparison there. So for some of the geometry, like I said before, the drill pipe, the tooling is really what's going to control the radius on almost every HDPE crossing. And I know there's a lot of rules of thumb for, 40 times the OD and stuff like that. And I think those are good, but we can also pretty easily calculate the actual bending stress and compare that with the allowable stress in the pipe, which is going to be somewhere, depending on duration, 1150 PSI to 13 or 1400 PSI, depending on the specifics of the project. So that is almost never going to be exceeded in HDD. So, but I like, the rules of thumb, they're good for real high level, but the math is really not that difficult. Or even if, everybody on the call here today isn't necessarily do that, you can say, hey, these rules of thumbs are great for feasibility and considering what are the options when it comes down to the actual installation. I definitely recommend, using the ASTM F1962 or PE handbook or one of those as a design guideline to run through those calculations. And here's a few of them. There's a lot of them: ASCE, NASTT, ASTM, PRCI, which is really focused around steel pipe, Plastic Pipe Institute. I mean, these are all good references. I definitely recommend these over versus someone who has written a book specifically. There's one I've got in mind, I won't mention, but it's been around a while, but there's a lot of errors in it that have never been corrected with a later edition. So if you didn't know they're there, you could maybe get into an awkward situation. So just talk a little bit about geology and geotechnical investigations and how they affect HDD and HDD design, construction. I like this picture because it kind of shows you a high level, looking at Texas here, which has got highly variable geology, depending on where you are. Coastal area, a lot of fat clays, getting into some sandy soils and silt, and then getting up into central Texas, you've got a lot of rock, limestone. That pink area, I think, is basalt or granite, and then it changes as you go north and to the west. So there's a lot of variability, but looking at the geology and asking your geotech engineer or recommending this to your clients, it's good to understand what soils you may or may not have, or rocks, how they were formed. It gives you insight into how you specify your field investigation and the types of tests you do, and to help budget it as well, because no one likes to spend money on this, although it's really the most important information for the whole design and construction. So it's always money well spent, and you can never get enough. So anyway, knowing this geology, you can specify your investigation program. And once you get that, you can do your lab testing. You can see here, this is a rock cores, a lot of fractures in it. And that's really good to know, because you're going to potentially have fluid seeping up through these fractures, which could just be a natural way to have a frac out, but not exceed normal pressures. So that's good to know up front. Let's see what we've got next. So another question I see a lot is, how many borings do we need? How deep do they need to be? A lot of times I'll say, we need to go down 75 feet, and that raises some eyebrows. I'm like, well, we know we need to be 40 to 50 foot anyway on a lot of these crossings, but if you happen to find some adverse soil conditions right in there, you might want to go 10 foot deeper. And you always want to get that information up front, because it's really difficult to go out again and drill another hole. And if these borings don't go as deep or deeper than the profile, you're basically designing a HDD with no information, or you're not telling the contractor what he's going to be drilling through. So that's a big problem. So we don't want to do that. As far as how many we need, typically every 500 feet or so is good, or one at entry, one at exit. If we think we've got some different things going on in the middle for short crossings, we might want to do one there as well. If we have very consistent materials, Fewer is okay because we're really just going to be confirming what we think we have. With complex geology or adverse conditions like a lot of gravels or boulders, things like that, we may want more so that we can better define how those adverse conditions can be avoided. And if we have a very definite soil to rock interface, we really want to define where that is. And that may make sense to have more borings so that we can see how that depth changes over the crossing. So that we can either be well above that or well below it, but not in that transition zone, because that just causes all kinds of problems while drilling the pilot hole and reaming and pullback. So want to avoid that. Yeah, so the information we want to find out is the type of soil, the amount of clay, sand, and silt. That'll have a big impact on the drilling fluids that are used. The type of rock, density, SPT, N values. You've probably seen those. Those are what are shown here. You know, it helps us kind of figure out, we want to have N values, say 10 to 20 or above are more favorable. They'll just have more strength and more weight to contain drilling fluid and better steering response, stuff like that. With the rock, UCS, that's compressive strength. That's directly correlated to penetration rates.
Hey Dave, how are you doing? Pretty good, pretty good.
Someone needs
I'm
to
actually on
mute there, please.
conference call, but I got it now. Probably that.
Also recovery and RQD, which kind of tell you how fractured the rock is, and how abrasive it is. So highly abrasive formations will obviously wear down your tools a lot faster. And whether you need 1 or 2, 3 drill bits or reamers or whatever to make a crossing is necessary to know that.
Well, I wonder if it's because they're paying so much business.
Hey, Rusty.
Rusty, you gotta mute yourself, bud. Hey, Steve, we had a question here. You typed in, how do you get soil borings in the middle of a waterway crossing? Well, that's a good question.
Yeah, so basically, which the most common way is to get a drill rig out on a geotechnical drill rig that is out on a barge and go out into the river. Obviously, it costs a little bit more. So most crossings, I'd say that if the water body is 200 foot or less, a lot of times they're just not even done. You get as close as you can to the bank and get those. But on long river crossings, you know, surely just get on a barge, go out and do the borings out there. That's very common. So what else we have here? Mohs hardness, that just gives you a relative hardness of the material to relate it to other projects, and most tooling providers for drill bits and reamers can give you an estimate on you know, how much wear, how many hours they can drill through certain materials. So that helps a little bit. And then for hydrofracture analysis, the unit weight of the soil, friction angle for sandy soils, cohesion for clay soils, and then there's some other parameters we need as well to calculate those things, but they're normally provided by the geotechnical engineer through correlations with the readily tested information. Some of the information, it's very difficult to get an accurate direct test on, so it's good enough. And I think a lot of these things, with experience, you start to get a basis of knowledge that you can relate new projects to old ones and start to predict and estimate what will happen pretty well. Other useful information, just any unusual stuff, karst geology. That's like the picture there with very porous limestone, pretty common in a lot of parts of the country. Porosity, faults, seismic activity, gravel, cobble boulders, pressurized aquifers. I've seen several of those this year and last year where we've started the pilot hole and groundwater starts flowing out of the hole. So there's a artesian condition there. Some were completely unknown and unexpected. Some were, you know, we knew it was a possibility and happened. One was actually near you, Alan, over in Cocoa Beach area. So it's kind of interesting. Geophysical testing, that's another thing that's done on some crossings. That is it's not cost prohibitive. It's a very good way to kind of connect the dots between your geotechnical borings. So it's more of a continuous test, and it gives you a lot of good information. It's really good for determining top of rock elevation. So if you have some very highly variable rock formation underground, that can really help immensely on that.
So with an aquifer condition that way, obviously you're not going to deplete the aquifer. Does it just make it so there's less friction, or you just have to deal with groundwater?
You know, all the ones I've seen, they've been pretty low flows. I'm talking like 5 gallons a minute, or, you know, something on that order. So I really don't think in most cases it affects the work too much. Excuse me. I think the real issue comes when, after you pull the pipe, if it continues to flow, how do you stop the flow? Because you basically drilled a water well that's flowing. So I think the common way is to, like you would pack off a water wells, to pump some thick bentonite slurry down there that will expand in the borehole, kind of like a water stop. And the idea is to stop the flow that way if it's not too high of a pressure, which mostly they're not. It's kind of an interesting thing.
Aquifer is all over the place here in Florida at 50 to 70 feet deep. So yeah, you drill into that real quick.
Yeah, sure did. Yeah. So next, once you got that information, you got a preliminary design. I like putting these borings on the profile so you can really kind of put all the information together on one picture. The plan and profile, one drawing, doesn't matter how long it is, adjust the scale as needed. And then you can see the whole thing, because the driller really needs to see the whole thing at one. You know, we see some of these drawings where you got 12 drawings to show the plan and profile, and it's like you can't put the whole picture together in your head that way. So this is really what I recommend, and I think most people would as well. We can see that, you know, here's that dark purple on the bottom of these borings, I think is a clay stone, and then above it it's more of just a hard clay. So we can kind of see where those interfaces are. We can see where the groundwater is up here, this blue line, entry and exit point. Kind of just gives you the whole picture right at one time. We've got some geotechnical information on these borings in here, but if you want more, you go to the report. To me, this really kind of brings everything together, and you can kind of plan it all out. Okay, next. Workspace. This is another issue. Obviously, the bigger the project is, the more space you need, and the more planning, easements, things like that you got to kind of work out to get set up before the project goes out to bid. This is a project up in Montana, and luckily the entry side here could be installed in a city park. It's for the city, a water main. So that worked out pretty well. But you can see you need a pretty big area for these projects if you're using a full-size rig. Now, a lot of them, like this one, this is actually for I'm trying to think, 24-inch water main. So not a real long crossing, but it's a smaller rig. I think that's probably like a 140 or a 100,000-pound machine set up in the side of the road. We put these Jersey barriers on the side to kind of keep the workspace and the travel lanes separated, and it worked fine, no problem. But obviously, I'm guessing that's about a 30 to 40 foot wide workspace. So you can have a track hoe in there to help put drill pipe on and off the thing, the rig. But this is something that really needs good thought, not only to place the equipment, but to get trucks in and out, access for bringing drill pipe back and forth, bringing cuttings and drill bentonite to the site, things like that. And that's sometimes it's pretty challenging. Exit side doesn't have to be as big. This is only, I mean, that dirt area is the width of this work area, and then it's swamp on both sides. So this is really narrow, maybe not even 30 feet, I don't think. They're pulling back a bundle of 4 10-inch and 4 10s and 2 4s HDPE conduits into a 30-inch casing. So that's a lot of work there. And this pipe's just laid out down a kind of a winding road there. Pipe, okay, this is larger. This is a 36-inch pipe. And I think everybody knows this, but HDPE is by far the best pipe to use when you have layout constraints. This is 100 times better than PVC or steel pipe for sure. Much more flexible, obviously, more forgiving material. So definitely a huge advantage when you've got site pipe layout constraints. I'm just kind of got all my problem topics on this one. So proximity to existing utilities. I see this a lot where people don't design these too much. They have the separation from utilities, kind of the same as you do with open cut or a jack and bore or something like that. I like 10-foot separation is just kind of a starting point for me, because you never know exactly on these deeper ones, especially if that elevation is maybe just a little bit off. And a lot of pipes like RCPs, their diameter conventions, I think, go by ID. So a 36-inch RCP, I think that's what it is. The ID is 36. The OD is like, I don't know, it's 54 or something like that. They have very thick walls, and the bells are even, larger diameter. So more space is definitely warranted. And then another thing is with especially RCP, they're short joint lengths. So you're likely to be drilling right under a joint. If that soil is weakened, we really don't want to have that pipe settle. Just all kinds of problems can start happening at that point. If that joint gets compromised, drilling fluid could go in there. No one's going to like that. And then I've also seen other utilities settle or just get damaged. And, obviously the more separation makes more sense. And yeah, I can't stress that enough. But also knowing the condition, I think, is important. I've had some projects where the utility owner, especially for like a storm sewer or something like that, they wanted to document the condition of that pipe with CCTV prior to installation just to document. And I think that's probably a good idea for everybody's liability, I guess, to document it before and after so that it can be demonstrated that it was or wasn't damaged. So a few risk considerations. These are all the results of risk happening. Just to kind of look at these pictures. This one is a barrel reamer. Whoops. A barrel reamer that just got completely torn up in a really fractured rock formation that I don't know what could have done. I wasn't involved in the design of that one, but I did see what the results were on the construction, and so that was obviously not a good outcome. The next one is a piece of broken drill pipe. This is 6-inch steel pipe with a right around a 1/2-inch wall thickness, and it's 135,000 psi yield steel. So incredibly strong product, and it was brand new, and that's what happened to it. So it just kind of gives you a good picture of the forces and stresses that are going on these projects and the things that can happen. So when we try to limit stress, I mean, this is why. Down here, this is a steel pipe, but I think it still demonstrates the same kind of risk that can happen. This is a kind of a really minor buckle in the pipe, but that makes it obviously unusable. So that had to be cut out and replaced. And this is a casing that was used. A lot of these projects, even for HDPE, you'll put in a conductor casing or a surface casing, maybe 100 feet, 150 feet, whatever, just to protect the soils in that area. Maybe you're going under a road, you don't have enough depth of cover. You put a casing in like this and then drill through it, ream through it, pull the pipe back through it. But on this one of the welds broke for some reason. No one knows why. We had to dig it up right in the middle of a state road. So that was very unfortunate. But these are just some of the things we're looking at. IFRs, frac outs, heave and subsidence, gravel, real soft clays, hard rock, geologic transitions, and tooling failures. I mean, these are all well-known situations. So knowing they're there is the first thing we got to do to make sure we can avoid them or mitigate them to the extent possible. And there are ways to do that. And and sometimes based on the specifics of these risk factors, HDD may not be the best installation method. Maybe a microtunnel or some other method that can manage the risks much better, even though if they cost more, possibly.
So Jim, just to give some cost discussion, if you want to go back, the slide, the excavation on the bottom right, could potentially be at least $250,000 if you're digging up a state road to go through that way. So that's fairly substantial and an oops to break this equipment in that standpoint.
Well, I can tell you on that one, it was 1.6 million to fix that problem. So yeah, ouch. Makes a big impact to your project, I'll tell you that.
It definitely would. Not a happy day.
No. But those things happen, and they're good. They're unfortunate, but they're good learning experiences, and you don't forget those very quickly. So with risk mitigation, some of the things, obviously using those design references, even if you've done this a lot, it's a good practice just to kind of go through like a checklist, even just to make sure you thought about everything. Talk to contractors, especially local ones who know the area and have worked extensively. just makes a lot of sense to think about how projects are built. You know, where we put the pipe, like, you know, like, and some of the other things I had in here, work areas and stuff like that. And ultimately, one of those guys has to build this. We can draw pictures and sell pipe and all that all day long, but at the end of the day, it all comes down to the contractor going out there and drilling and pulling pipe. So makes sense to work with those guys and listen to their advice. And then when we know there's risks based on geotechnical, IRs, pipe issues, we gotta have an answer for that. We can't just kick that down the road and say, well, we know it's a problem, but we're gonna have you fix that problem. I mean, that's just not a good way to do it. Doesn't mean your solution is the only solution, but if you can't think of one, then you know that just doesn't set up a good scenario for a good project. And you know, on the other side of that, this is a small frac out right here in this picture. That's small. It's in a you know, a field right maybe 30, 40 foot in front of the drill rig on the entry side. On this project, that was nothing more than a nuisance. Just did not even really matter at all, because they had to excavate this area. Whoops. They had to excavate this area to do a tie-in anyway. So it's kind of like, who cares? In other cases, it's something near the end of the world to some people. So, you know, it's always a case-by-case basis. And this is not really unexpected here because we've got really soft clays. They just will not hold their shape in a hole until you get to substantial depth. So as they drill this pilot hole, once they get out past that, the ground closer to the rig that was shallow would start to collapse and kind of constrict the hole. So the fluid, when it's pumped down there, it's got to go somewhere. So that's the result here. So talk a little bit about pipe. So
Steve,
this, I think,
I had asked a question about when we might use fusible PVC as a preference over high density polyethylene. So as you develop this, Jim, just and find a time, maybe you can address that question.
Yeah, that's a good question. Yeah, I work with all types of pipe. I've done a lot of PVC projects. To me, the best application for those is where you need a lot of tensile strength. And I mean, we all know PVC has got a higher tensile strength than HDPE. So I've done I think 3 7,000 foot crossings with PVC. Those are the longest ones I know of. Did a 4-inch PVC line that was over 1 mile long, pulled by itself. You know, I think just the material properties, you know, today or in the past 5 years or whatever, that's the difference between those two materials. I know some people have preferences, but as far as just HDD and installing the pipe, not worrying about what the pipe's used for, that's the big difference. I am starting to see HDPE, I think they're bumping up the diameters and the DRs on some sizes, and we're seeing some projects that I would say just 3 or 4 years ago would have been no way. Now they're being considered. I just think the industry keeps pushing forward, and I think we can keep expanding the limits of what HDPE can do, because, you know, 98% of the time when a project doesn't work, for whatever reason, it's not the pipe's fault. It was either a misapplication, the hole wasn't drilled very well, there was some other some other circumstance other than the actual pipe itself. So I think I think they could be done. I think we can expand what has been done to date. And I've seen, we're always trying to figure out what's the longest one so that if somebody's got an application, we can say, hey, see, it's been done here before. Because a lot of, especially in the municipal world, a lot of them, they don't want to be the first one to try something. And I say, I've spent my whole career doing stuff for the first time. And, most of the time it works out. You just got to think through and plan it out. Not 100% of the time, but you have to balance the risk with benefits. If it's a huge benefit for the owner, maybe it's worth the risk, but it's different for everybody. But I think what's interesting here is 50% of HDD is HDPE. I wouldn't be surprised if it's actually more than that. But anyway, it's a good, obviously a very good market share. And like I mentioned before, the flexibility is just such a huge advantage. You can't overstate that. You could never do this with PVC or steel. Just wouldn't even be consideration. So benefits, I think you guys mostly know this. Great for friction, very low. Pullback forces, I'd say that depends. I promote ballasting pipe in most situations, because typically when you look at ballast it, meaning fully fill it with water during pullback continuously versus empty pipe, the pullback when it's ballasted is usually going to be right around 1/3 of empty. And a lot of contractors just think, oh man, that's a big pain, it's just whatever. On smaller projects, I agree, it's just not necessary. But when you get up to some certain point, things you can control above ground through planning before the project, before that pullback day, anything you can do is that, and you can control it, is definitely better than let's give it a try. You're pulling back, you're halfway through, and you're getting close to, hey, this thing should be coming a lot easier. We're getting close to this, the rig capacity or the pipe tensile capacity, something like that. Then you're right in the middle of it. Your options are very limited. If you get the pipe stuck, then what do? You can try to pull it back out. There's some different things, but things you can do like ballasting, it just makes a whole lot of sense. Definitely a good risk reducing action. Scratch and gouge resistant, that's a big advantage. Impact, fusions, all these things are great for HDPE. PVC is good too, but the thing about it is you've got to be really careful with PVC above ground. I've seen a lot of situations where the pipe is, it really has to have really good support on any kind of bends. So having like one, say, excavator with a cradle or something where that pipe comes in and then makes that bend, as your length increases, those tensile forces increase. And then when you have a fused joint come through there, it's a stiffer point. So you've got a stress concentration, and I've seen quite a few of them break. It's just kind of a characteristic of that pipe, but I think, most people aren't ready for the requirements of supporting it above ground. And that's what happens. So here's a project. This is down in Miami. I worked on this. This is at least, I want to say about 10 years ago. You can see the pipe laid out around, and it actually comes all the way back and makes a whole loop. So that's obviously for this project, a single string is definitely more desirable than having multiple. multiple strings where those fuses have to be made on pullback. I mean, those are, I'd say at least a 2-hour stop to fuse, sometimes more than that. It all kind of depends on the setup. But a single pipe is definitely more advantageous. And this is the only pipe that could do that. I think this is a 30-inch force main going in here, maybe a water main, I can't remember. Yeah, I guess that's water with the blue stripe. I also did one in Key West a few years ago. We had a bundle, I think 2 8s and 2 6s and a 4, and we were in a similar situation. We looped it around just like this, and it was the only way to do it there. So that was a big advantage. Some more pictures kind of demonstrating advantages of that flexibility. Couple more. And here's PVC, and actually I worked on these too. These are this one's in South Carolina on the left. That's a 16-inch PVC, and the two on the middle and the right are 30-inch PVC in Port St. Lucie, Florida. And the pipe layout was one of the most challenging aspects of most of these projects. I mean, they were both 7,000 feet. You just don't find 7,000 feet of straight line pipe layout for many projects. You know, it's the one on the right, the 30-inch, it went up over this mangrove swamp, which obviously mangroves in Florida are like the most precious thing you can think of from an environmental standpoint. So you can't touch them or cut them or anything. So you had to go up and over, see all these cranes. Then the pipe's laid out through the water for about, I don't know, half a mile around a big curve, and then it turns 90 degrees and lays out along the road. So I don't know, it's the layout and pipe management on this has probably cost, I don't know how many millions of dollars, just huge cost to do this. This one too, it was fairly straight, but you know, the break I was mentioning a minute ago on the fuse happened on this project with just a really small little horizontal bend in the layout, because you've got 5,000 feet of pipe behind you, creating a lot of tension in that pipe. So the bending stress is going to be much higher. So I don't know if HDPE was, you know, worth considering for this project, but if it were, these things, you know, the handling of the pipe and the layout would have been much easier. So some tooling discussion. So in pilot hole, I'll stop there. Any questions on what we covered so far? Or I guess we could do questions at the end, whatever works. So drilling a pilot hole, there's really two ways, jetting or using a mud motor. And that's really just comes down to how hard the ground is. So usually soils up to blow counts somewhere in the 30 to 50 range. So you're getting up to pretty dense soils. You can jet, and different contractors have a different point that they're going to switch over to a mud motor. So this is easier to drill from a steering standpoint. But as that soil becomes more and more dense, you're just slowing down and slowing down to the point where you can't do it. So then you switch over to a mud motor. And obviously for rock, you'd use that as well. So the real difference there is when you're using a mud motor, this drill bit is rotating continuously. Whereas when you're jetting, if you want to steer, you got to stop and just push it through the soil. So really don't have any drilling going on. But with the mud motor, you've got also either a bent sub, which is just a piece of pipe that's got about a 1 to 2.5 degree bend in it, or the motor can have a bend in it itself to kind of combine both of those into one piece of equipment. Reamers. there's probably 1,000 different types. These are good for mixing the bentonite slurry with the soil cuttings to mix those up really well, as is this one. This one's a little bit more, will help compact the soil off into the sides of the drilled hole there. Here's another, there's just many different types. And then you got people make their own things. I don't quite know exactly what this is, but there's a lot of, everybody's got their own homemade versions. And then there's hole openers that have like the drill bit roller cones or something like that attached in a radially on it for harder material. Here's a pull head. This is kind of typical for bundle pullbacks, using a couple shackles and just kind of a shroud type apparatus here to kind of pull those together. Works pretty well. And for larger pipe, this is steel pipe, I think, maybe, but steel pull head, big shackles. This is a swivel. And then the drill pipe will be hooked up to the other side of that swivel. Another way this is done is by using, it's called either like a knuckle joint or a U-joint, something like that. So it's more of a fabricated steel device that is pinned like this to connect the swivel to the pull head. So shackles really aren't designed for this application, although they work fine. So it's a little bit of a preference. Sometimes it'll be specified which to use, but these if they're rated appropriately for the pullback, they can be used as well.
Yeah,
So
that's got to be some really stout stuff there. I mean, to withstand the pulling forces there, that's just hardened steel. They've got to make sure they're well maintained as well. You don't want that breaking when you're down in the hole, right?
Exactly. Yeah. So, you can go, I think it's a good idea to inspect the welds on some of this stuff, and especially, these roller cones. I like these because you can see they're attached on both ends. Sometimes they get like a drill bit, and it's called a split bit hole opener, and they're only attached at one side, so that the bearings have to take all the force on one side. So obviously there's a lot more force that comes into play there, and they're designed to do it, but it's not unheard of at all for those roller cones to break off and just be left in the hole somewhere, which obviously is not going to be compatible with pipe being pulled through there later. So you got to go in there and use a magnet or a basket or something to extract those from the hole. So it really makes sense to have these inspected. Basically everything that goes down hole should be carefully inspected. Take a picture of it, measure it. Another thing, if you're in hard rock, you're going to wear on this material. So say like this little one, it's I don't know, say it's 24 inches. You got to drill that 24 inches so that this guiding part of this hole opener will fit in there, because this isn't going to cut anything. It's got to fit into the hole from the previous one. But if this thing wears so much that the hole, when it exits, is an inch smaller diameter because you've worn so much of the material away, this thing's not going to make it all the way across. So you really have to think about how this all works together and why you're doing one for the next, and how they all kind of work together. Whoops. Yeah, so that's that one. And then just about done here. The last one is going to talk about some of the design software. This is Boraid. I think there's 2 versions. I don't use this myself, but I think one you can download for free, and then there's one that's got a lot more functionality that you pay for. My thought, I do this all the time. So I've kind of got my own spreadsheets. I calculate and everything. So it makes it easy for, you know, if you have something unusual, it's easy to just manipulate a spreadsheet to accommodate whatever situation you have going on. These are a little bit more based on minimal parameters that you can adjust. So that's really my only criticism of them, is that they don't have enough flexibility in some cases. But I think it is good to have just kind of a quick idea of of what your pull loads and all that will be. But like everything, you really have to understand the input you're putting in there, and what that means in the big picture. A couple of weeks ago, I was working with a contractor, and they had something similar to this, is a little different, and they were getting some numbers as results that just made no sense. It was like, say you're pulling 2,000 feet of 20-inch DR9. They had a pull load estimate of like 1,500 pounds. I'm like, that, I mean, that doesn't pass the common sense test, you know. I mean, you gotta have a feel for what the results will be, because sometimes, you know, it's a computer. The code will get screwed up. If you got a spreadsheet, you've copied the wrong cell or just deleted something, or, you know, all kinds of things can happen. So having a backup check, or at least just a real high level, does that sound right? I mean, 2,000 feet of that pipe is, I don't know what that weighs, 100,000 pounds, 200,000 pounds of pipe. So to say a pull load is 1,500 pounds, that just doesn't make any sense at all. And so they went back to the drawing board to figure that out. I don't know what the outcome was, but to me, that's kind of the risk with these things. I think they can be a huge help, but when you don't know what the outcome range should be, there's a little bit of a risk there. But other than that, I think it's a good help.
This is one of their homework assignments, Jim. They have to work through Boraid. So,
okay, good.
One of 5 options. It's a good thing you covered it here.
Yeah, and I would say, you know, the PE handbook, I think is it chapter 12 on HDD? Maybe, I can't remember exactly. You know, it's been around for a long time, but it's a really good resource, as well as the ASTM specification, which is based on HDPE pipe. That one's really good too. I mean, I go back to those all the time. I mean, they're just great resources. You know, they don't always apply for every situation, and you're going to run into some projects that just have some unique characteristics that you've got to go outside of these standards or whatever. And you know, especially when you're looking at installation conditions, and then looking at post-installation condition, but prior to placing in service, and then you have the testing conditions. There's a lot of different parameters there, and I see a lot of people, sometimes they're not really thinking about what you're actually doing to the pipe. They're looking at kind of more of a generic scenario and calculating, say, this pipe doesn't work for this situation. And then when you really look into, well, what are we really going to do? What is our test pressure? Not, you know, you have to look at those parameters and think about them, and make sure that you're not excluding, you know, using this pipe sometimes, or maybe saying, well, we got to use a DR7 because this one little situation, and maybe otherwise you'd have been doing using a DR11. I mean, not a huge thing, but maybe that's a pipe size change that you have to look at, and that, you know, the cost can go up unnecessarily. So I think that's it. The end. Any questions?
No, excellent job. That was good information, especially to know where, PVC is winning out over poly, and it makes complete sense when it comes to tensile strength. The longer the pull, the harder you got to pull on it. And sometimes it's just beyond the capabilities of polyethylene. So it's good to know when that's the case.